Hello, physicists. Today we're moving into a whole new unit that is called angular motion. And the beauty about angular motion is so much of the angular motion really mirrors or parallels the linear motion that we've done. So angular motion is any object that is moving in a circle, whether it is rotating or whether it is going around another object like that. So whether it's spinning around its own axis or whether it's rotating around some other axis. So when we talk about this, we want to go through just sort of the broad general ideas and work through a couple maybe sample problems here to give you an idea that is like the basics of how this is going to go. So if you think through the similarities we have in linear motion, I'm going to write the word linear up here, and on this side I'm going to write the word angular. So we have linear motion and we have angular motion. So I have position, and to convert that, I'm going to say that my angular position is going to be theta. So it's going to be how much around the circle you go, which will be some kind of an angle, right? Then we can say there is a velocity and an acceleration. Our velocity and our acceleration are going to have the same mirrored values. We'll have our velocity, we'll have an angular velocity called omega, and we'll have an acceleration that's an angular acceleration called alpha. And the way we would convert all of these linear values is these angular values is we're multiplying times the radius in order to get the linear value. Now, one of the reasons we can say that is if you think through how many radians or how many, let's see, I just gave it away. How do we measure our angle? We either measure our angle in a couple different ways. One of those is going to be 2 pi radians, which is how far around the circle it goes. So one time around the circle is 2 pi radians. Another way we can measure it is 360 degrees. And we could also call that as 1 revolution. Okay, now that's part of the confusing thing about this particular unit is there are so many different units you can use for this. We're going to default mostly to radians. So anytime the problem gives you anything other than that, you're going to have to put it back into radians. Now, why do we use radians? Radians technically is not a unit. So 1 loop around the circle is 2 pi. No radians, but we say radians just to give everyone an idea of what that is. Now, is that a better unit? I would argue it is, because there is no unit. There is no value there, as opposed to degrees. If there's a degree, I have to get rid of that unit in order to do anything. So when you think through it, the problem, though, is you would never launch a rocket at like 3/5 pi radians. You would launch it at some kind of a degrees, right? So the standard in engineering is going to be the degrees, but we're going to look at the radians here. So when I do that, think through the fact that all of these, like for instance, the theta value, it doesn't have a unit. So in order to make our linear value in meters, we have to multiply it by a meters unit, and that's where we're multiplying by our radius here to get the position. The next one you can think through, this angular velocity is going to be radians per second. So I'm going to put radians per second here. Again, that's the same as saying 1/seconds, which means that in order to make this be a meters per second, I have to multiply it by meters. Another way you would see this is RPMs, or revolutions per minute. And then when we talk about our angular acceleration, this is going to be radians per second squared, right? And so again, in order to convert the radians per second, or 1/second squared, into meters per second squared, we have to multiply it by that value that is in meters. And that's why we convert by multiplying by the radius. Now, whenever we get into the next chapter that we covered, so if you think through, we covered those are the kinematics values. The next thing we covered was dynamics. And so we're talking forces. And we're going to say that the force that causes an object to rotate is what we would call torque. And in order to get the torque, we're going to have a radius times a force. So notice in this case, our radius flip-flops over to the linear value in order to get that. And our unit is going to match the value that is that radius times a force. It's going to be Newton meters, or newtons times meters. Then the next thing that we want to talk about is we're going to talk about kinetic energy. So we went into energy after we did the dynamics. So we would say that our K trans is related to our K rotational. Okay, they're not equal, not like equal in the above here, but that's sort of the analogous part of it. Is we have our kinetic translational energy, we have our rotational our rotational kinetic energy. What do we measure any energy in? That is still going to be measured in joules. So any energy is measured in joules. Then we would have, after we talked about energy, we went into momentum. So we want to talk about the different kind of momentum. We would have a linear momentum, which remember was a P. And if I multiply that by a radius, then I'm going to get my angular momentum, which is an L. And that's really what that guy is. The unit for it is going to be the kilogram meters squared per second. It's not a renamed unit, so it's going to go with that value. Now, there's one more thing that we probably want to talk about, and that is going to be inertia. So if you remember, there's an inertia that goes with a lot of these, especially as we get into the further ones in the semester. And remember that inertia is measured by mass. It's how much an object wants to resist its change in motion. So when we talk about rotational objects, the difference between linear and angular angular inertia is that in linear inertia, we only have the mass of the object. But in rotational inertia, where the mass is located plays a really, really big role in how the object is going to spin. You know, picture if I have a baseball bat and I'm trying to spin the baseball bat from the end that I would hold, or I'm trying to spin the baseball bat from the middle, or I'm trying to spin the baseball bat from the end that is heavier. All three of those are they're gonna cost me, or it's going to be different for me to spin it in each one of those ways because of where that mass is located. So the same way that the kinetic energy is analogous to the translational to the rotational, we're going to have an inertia that is analogous, that is going to be I, and that's what we will call the moment of inertia. So we'll talk more about this later, but in general, this is the form for it. And then you can see all of these different ones here that for now, until we learn how to derive those, you can just look at these and say, okay, that's how I'm going to find the moment of inertia of that specific object. Okay, so from there, we can take and say, hey, our linear equations are going to mirror our angular equations. So if I have my three kinematic equations, x equals VIT plus 1/2 AT squared, VF equals VI plus AT, and VF squared equals VI squared plus 2AX, then I can literally take and substitute in my angular values for each of those to get the angular equation. So if you recognize the linear ones, it'll be really easy for you to get the angular ones. So my angular position is theta. My angular initial velocity will be omega I. So remember, I'm going off of these values up here that are sort of the angular versus the linear. Then my time is going to be the same no matter what value. Remember, we talked about that in dimensions also. And then I'm going to have 1/2 of alpha t squared. Next one's going to be the same thing. Omega f, so the final angular velocity, equals the initial angular velocity plus alpha t, or the angular acceleration times time. And then we can say that last one will be omega f squared, omega I squared plus 2 alpha theta. So notice that the equations mirror each other, so that makes it really, really, really simple. Okay, when we move into linear dynamics and talk about forces, remember we had one really super major equation, and that was Newton's second law. So we would say F equals ma. So we can do the same thing when we talk about angular. We can say the torque is equal to, now remember, what does inertia represent in angular? The inertia is represented by the moment of inertia, which is I, and then our acceleration is going to be alpha. Okay, so we're going to have I alpha. When we look at that, we can simplify this down just a little bit and say, well, hey, in general, for a point mass, our I value is mr squared. So I'm going to say this will be torque is equal to mr squared. And my alpha, if I think up here, is really going to be A over R. So I'm going to take this and say A over R. And whenever I get rid of one of my R's there, I'm going to be left with a torque is equal to a force times a radius. Hey, isn't that what we set up here? Torque is equal to a force times a radius. So I can take and put these two together and say that torque is equal to I alpha, which is equal to force times radius, and that becomes my angular equation for torque. Isn't this cool the way it fits together? Okay, so next one then, we're going to talk about energy. So if I have a kinetic translational, so remember translational means linear, energy is equal to, remember it's 1/2 mv squared. What is my kinetic rotational equation going to be? Okay, it mirrors this one, 1/2. What's the mirror for the inertia? Is going to be I. And what's the mirror for the velocity? It's going to be omega, and then we square it. And so that's my rotational kinetic energy, 1/2 I omega squared. So I hope you're seeing how this basics becomes super easy because it just mirrors everything we did with linear. So as you build on the angular, try and think to the linear. How did it work in linear? And then use that to your advantage. Same thing for linear momentum. Remember that was mass times velocity. So whenever I do my angular momentum, which is an L, I can say my angular mass or inertia is the moment of inertia, and my angular velocity is that omega symbol. So I omega is going to be my angular velocity. Now, we can do the same thing that we did up here with torque, where we plug some values in. So let's say equals mr squared. And then isn't my omega value, if I think back to what I had up here, my omega is going to be V over R, right? So V over R. Again, one of my R's will cancel out, and I'll be left with an angular momentum of mRV or MVR. And hey, what is m times v? Isn't that linear momentum? So I'm going to have the same equation RP that I have up there, and I hope you can see how this is just really cool. So I have my I omega or RP, and depending on what I have, then that's how I'm going to use it. So if I'm dealing with something rotating, then I can use the angular part of that equation. And if I'm dealing with something moving in a linear direction, I can use the linear part of that equation. So that's a nutshell of how to do these mirror each other, and how you can take and think of linear and angular to mesh the two together from that. And here in a second, what we'll do is we'll work out a sample problem that just walks all the way down through each of those. So now in this part, what we want to do is walk through a sample problem that would cover each of these different topics for the momentum, for angular motion. So a potter begins rotating their 76.7 kilogram pottery. So I'm going to highlight that because that's going to be my mass. After 15 seconds, the wheel is spinning at 60 RPMs. And if the wheel has a radius of 0.55 meters, that's going to be the basis for this entire problem. So the first thing that I noticed in that, I noticed that these are in units that are all good, kilograms, seconds, meters, except for this 60 RPMs. The 60 RPMs, I want that to be in radians per second. So I'm going to start here with 60 RPM. And remember that RPM is the same as revolutions per minute. So what I'm going to do then is I'm going to do a dimensional analysis where I take and I get rid of my revolutions. And remember that one revolution around is going to be the same as 2 pi radians. And then I want to convert from minutes to seconds. So I'm going to get my minutes in the numerator and my seconds in the denominator, and I'll have 60 seconds to a minute. And once I convert that, then I know that my spinning value is going to be 6.28 radians per second. Radians per second. Okay, so now what is the moment of inertia of the wheel? So what we would do is we would consider this wheel itself to be a solid cylinder. So it looks like I'm going to have this solid cylinder, which is going to be right here, cylinder that's solid, 1/2 mr squared. So I have I is equal to 1/2 mr squared. I might want to write somewhere here that this is a solid cylinder, so that later I would remember that. And so I'm going to place in 1/2. I know the mass of the wheel is 76.7. And I'm given the radius of the wheel also is the 0.55 and then don't forget to square that. So whenever we put that in our calculator, we end up with a value of 11.6, and kilograms meters squared is going to be my inertia value there, okay? So 11.6 kilogram meters squared. Now, I also want to find out what is the moment of inertia of the 0.2 kilogram piece of clay on the wheel. So I'm going to put the 0.2 piece of kilogram there. And we're going to assume that the 0.2 piece of clay is out on the edge of the wheel to begin with. So there's a moment of inertia here where it's going to be the same as a point mass. Okay, so it's going to be the same as a point mass. And that I value for a point mass is going to be mr squared. And so when I plug in my values, I'm going to have the 0.2 kilograms. I'm going to have the radius that is the 0.55, and then don't forget to square it. So I end up with a moment of inertia of the clay that is going to be 0.0605 kilogram meters squared. Okay, so I end up with two different moments of inertia there. Now, moving into the kinematics value, what is the wheel's angular acceleration? So when I'm talking about the acceleration, I have to look at that and say, okay, well, what am I given? What do I know? Well, I know that after 15 seconds, the wheel is spinning at this many RPMs or this many radians per second. So I know my initial angular velocity is 0. I know my final angular velocity is that 6.28 radians per second. And I know that the time it took to get up to that value was 15 seconds. And I'm looking for the angular acceleration. So then what equation has two velocities, a time, and an acceleration in it? And you could think through linearly, we know that it would be this one. So angularly, it has to be the mirrored value of that. So I'm going to say omega f equals omega I plus alpha t, 6.28. The initial velocity is 0. My time is 15, and my acceleration is what I'm looking for. So whenever I divide that, I get a 0.419 radians per second squared as my angular acceleration. So then what distance will the piece of clay on the edge of the wheel travel during this time? So if I'm looking for distance, I've got to be looking at one of these two equations that have distance in it, the angular version of those, the theta values. So if I do theta equals omega t plus 1/2 alpha t squared, I'm looking for theta. My initial velocity was 0, half of that acceleration, 0.419, and times the time of 15 squared. And when we do that, we get 47.1. And again, what do we measure that angle in? Everything is going to be in radians, assuming that you put everything at the beginning in the radians per second squared, etc. Okay, now, how would we find the linear distance of that? There is one easy way to do that, and that would be, if you remember up here, that converting angular distance to linear distance, I can do x is equal to r theta. So I can take the radius, which is 0.55, times that theta value, 47.1 radians. So the 0.55 was in meters. This is in radians. Remember, radians is not a unit, and so it goes away. And when I multiply those, I'm left with the value of meters, and I would have a linear distance of 25.9 meters. Now, another thing that we could do is we could take and put this linear distance into the equation, x equals VIT plus 1/2 AT squared, right? And again, we can say the initial linear velocity is 0. I'm looking for this x value, 1/2. And if I convert my angular acceleration into linear acceleration, so I'm going to take 0.55, which is my radius, times my angular acceleration, 0.419, and then times the time squared, 15, was it 15? Yeah, 15 squared. And when we do that, hey, guess what we get? We get 25.9 meters. So it shows you that you can solve this linearly or angularly and then just convert one or the other, whichever way makes sense to you. Now, moving into dynamics. If the potter pushes a wet rag against the wheel with an inward force of 40 newtons, so that's going to be a given that I have, an inward force of 40 newtons, and stops the wheel in 7 seconds, what is the coefficient of friction between the wheel and the rag? Okay, so I'm looking for coefficient of friction. I'm mentally thinking through that, saying at some point I'm going to have to say the force of friction is mu force normal, right? So the force of friction is mu force normal, which means that I'm looking at a torque on this because I'm dealing with forces. So I'm going to start with my equation. Torque equals I alpha equals FR. It looks like that force that's applying the torque is going to be the force of friction. So I can plug in this mu force normal times the radius. And when I do that, then isn't the normal force this force that the potter is pushing inward on the wheel? So the wheel is spinning this way, but the potter is pushing perpendicular to the wheel. And so that value, that 40 newtons, is going to be my normal force. So on this side of the equation, I have mu, I have this value of 40, and I also have the radius of 0.55 meters. Okay, now that doesn't help me solve for mu unless I know the other side of the equation, which is going to be either the torques or the I alpha values. Now, didn't we find the I value up above to be 11.6? So I'm going to take and say 11.6 here. And now the next thing we want to talk about is, hey, how would we find this alpha value? So it looks like we're going to have to go back to kinematics up here. Like, what's the deceleration of the wheel because the potter is pushing in on the wheel, slowing the wheel down. So I would say probably that the final velocity will be 0. The initial angular velocity will be whatever we calculated up above, the 6.28 radians per second. The time that it takes, they give us is the 7 seconds, so 7 seconds, which means then we're looking for alpha. So what equation has those in it? It looks like it's going to be the same equation we used above. Omega F equals omega I plus alpha T. So I have a final velocity of 0, an initial velocity of 6.28 plus alpha times 7, and that gives me a deceleration of 0.897 radians per second squared. Then I can plug that in over here, 0.897, and solve for my mu value. So when I do that, I end up with a coefficient of friction of 0.473 as my coefficient of friction. Now, how much kinetic rotational energy does the wheel have? Okay, so if we're looking at rotational kinetic energy, we're going to be doing this k rot rotational 1/2 I omega squared. So while this is spinning before it stops, then we could say that this is going to be 1/2 of 11.6 that we calculated above. The radians, 6.28 radians per second squared, and then square that, radians per second, and then square that. So our rotational kinetic energy is going to come out to be 229 joules. How much rotational kinetic energy does the piece of clay on the edge have? So if we take and we put our clay back on after we've stopped the wheel, now we spin it back up again under the same conditions. So we're going to have a rotational value for the clay, 1/2 I omega squared. But remember, it had a slightly different I value. So we're going to plug in its I value, 0.0605, and the same velocity, 6.28 squared. So we end up with a rotational kinetic energy for it of 0.00915 joules. And that gives you the kinetic energy that the clay would have on the edge of the disc. Now, how much angular momentum does the wheel have? So again, I'm going to start with L equals I omega equals RP. And from that, which ones do we know? Do we know the I and the omega, or the R and the P? Or what's happening? Is this spinning, or is this object moving in a straight line? Well, it's spinning, and we have both this the moment of inertia and the angular velocity. So I can plug in the moment of inertia, 11.6. I can plug in the angular velocity, the 6.28, and solve for a angular momentum of 72.8 kilogram meters squared per second. And so that's going to be the angular momentum of the wheel. Now remember, momentum tells you how much an object is wanting to keep rotating or not rotating. It's like the quantity of motion. So this is telling you how much, the keep wanting to rotate or not wanting to rotate is really the inertia, but the momentum is telling you how much motion is there from the rotation of that wheel. Now, how much angular momentum does the piece of clay have? The piece of clay, we can do RP equals I omega. And again, it is also rotating on the wheel. So it's on the edge of the wheel here, rotating around. And we have that moment of inertia is 0.0605. We have that angular velocity, which was the 6.28. And we can find the angular momentum of it to be 0.38 kilogram meters per second squared. So what we have then is how this all fits into one big angular problem, angular motion problem, where we can start with the moment of inertia, which is how much an object wants to keep moving or not move, the kinematics, then into, which describes the motion, then into the dynamics, which deals with the forces behind it, then into the energy of the object, and at the end then how much momentum the object has. So this is just one way, one example that fits all of that together. Obviously, there are a bunch of different ways that we can take side rabbit trails to get different values. This gives you just a summary or overview of how everything kind of fits together.